Okay, let's get started. This is lecture 17. We're starting a new kind of unit here, a short unit on like linear programming and semi-definite programming, which will extend into a longer meeting or longer unit on constraint satisfaction problems and hierarchies and some other things. Okay, so as always, I'll put up some resources here. A nice simple book. There's many books, but a nice simple book about linear programming is this one by Matoušek and Gärtner. And if you want the full details on every possible aspect of the theory of linear programming, you can check the Grötschel, Lovász, Schrijver book at the bottom. Okay, so linear programming. I know you probably know something about it, but we're going to go over it again because it's definitely the greatest polynomial time algorithm. Let's just be honest about it. It's fantastic. Actually, there's a bit of a not misnomer, but I said it not quite correctly. Linear programming is not an algorithm. It's a problem. But the fact that this problem is solvable in polynomial time is, in my opinion, the greatest fact in algorithms theory, because so many things can be done with linear programming, and it's really great. Okay, so what is the linear programming problem? The input to the linear programming problem is a list of inequalities. Okay, so when you're solving a system of linear equations, you have a list of equations in variables x1 through xn. Here we have a list of inequalities in equations. In, let's say, n variables and m unknowns. And you can think of everything happening over the reals, but since you're supposed to be given this as an input to a digital computer, we assume that the coefficients, the a's and the b's, are all rational numbers represented as just pairs of integers, numerator and denominator. Okay, that's the input. And there's a geometric interpretation to it. So for every inequality like this a1 x1 plus a2 x2 plus ... plus an xn, that's geometrically a half space. The set of the points in real space that satisfy this is a half space. So if you had equality like a1 x1 plus ... plus an xn equals b, that's a half plane or a hyperplane. Okay, and the inequality gives you everything on one side of that hyperplane. And so K is supposed to represent the conjunction of these. So we have a sort of a conjunction or intersection, if you will, of hyperplanes. And their intersection is the set K. It's like a polytope represented by these inequalities. Now, sometimes you might have lots of inequalities, but the intersection of all of them might be empty. So I put this green inequality up here. And if you look at the green inequality, it misses the triangle that was formerly K. So it's possible that the intersection of all these inequalities leaves nothing. And in some sense, this is the linear programming problem to tell, is there a, is this K the empty set, or is there at least one point in it? Okay, so that's the input. And yeah, so it looks a little bit oversimplified because I only have inequalities. But you can make a few variants on this, as you possibly know. So if you want to have less than or equal to, instead of greater than or equal to, well, you can do that just by negating the inequality. If you want to have equalities instead of just inequalities, or a mix of inequalities and equalities, that's no problem as well. You can just put in two inequalities in both directions, less than or equal to and greater than or equal to. If you want to have strict inequality, well, can't have it. Sorry about that, but that's one thing that's not allowed. We always want to just have greater than or equal to in these linear programming problems. And you might be most familiar with linear programming, not as just, you're given a bunch of inequalities and you want to know, can they be satisfied or not? Is there a point in the intersection of all these half spaces? But rather it's a problem of, given a bunch of inequalities, to maximize a linear form like this c dot x here, subject to these inequalities. And this is also called linear programming, and you can do that too, but we'll get there a little bit later. For the purposes so far, we'll just stick with this question about, given some inequalities, can they be satisfied simultaneously or not? Okay, are there any questions at this point? Okay, not hearing anything. Hopefully you can all still follow along as I go. Okay, right, so you can think of this as a decision problem. Given these inequalities, just decide yes or no, is there a solution to all of them? But you might ask for a bit more. For example, if the answer is yes, there's at least one solution, k is not empty, then the natural question is to actually find a point x that satisfies all the inequalities. And interestingly enough, if k is the empty set, you shouldn't, ideally just say, yep, it's empty. What would be really great out of an algorithm given such a k would be to output a proof that there's no solution to these inequalities. And in fact, we're going to talk about how that's possible. But we'll come back to that, exactly what a proof is. I should remind you, or what I want to tell you though, is this problem, as stated, the linear programming problem, is solvable in polynomial time. And that's a wonderful fact that we're going to actually take for granted in this lecture, but we'll talk about it in subsequent lectures. This was first proved by Khachiyan in 1979. It was the USSR time, so he's, I suppose, a Soviet person, although you can tell he's of Armenian heritage from his surname. He was actually a PhD student at the time when he solved this. It's a little bit funny, though, because he solved it using an algorithm called the ellipsoid algorithm, which we'll talk about later. In the 50s and 60s, when this was studied, a lot in America and other places, they didn't know if it was polynomial time solvable or not, but they had a different algorithm, the simplex algorithm, which they seemed to think worked well in practice. But it was a big question of whether you could actually solve it, in P. And you can, thanks to Khachiyan's work. As I said, though, he used this thing called the ellipsoid algorithm, which was originally developed by Naum Shor in the early 70s and uses a tool for convex optimization by Nemirovsky and Yudin in the 70s. And I think they were more practically minded, and they weren't really thinking about oh, let's see if it shows that linear programming is solvable in P on a Turing machine. So the ideas and techniques date back to these works, but Khachiyan published in 1979 a proof that it's in P. Actually, he didn't give the proofs. He just gave the sketch of how it worked. And it wasn't until everybody in the West got excited about this, and particularly these two Hungarian guys who are a nice bridge between the East and West, Gotz and Lovász. They kind of read his work and figured out how to fill in the gaps in the proof. So maybe they were the first to publish a proof, although in 81, Khachiyan published the full details of his proof. And I should also mention shortly thereafter, Grötschel, Lovász, and Schrijver showed that you can do many other related things in polynomial time, like find vertices and optimize even with a separation oracle and all these other things that we'll eventually get into. I just want to briefly say that, it's funny to think about, but it was, 40 years ago? It was really big news back then. So this is the front page of the New York Times in November, December 1979. You can say down here, it was front page news. A Soviet discovery rocks the world of mathematics. It was about Khachiyan's paper. So you can, I don't know, take a look at these slides afterwards. Actually, I thought it was a little bit funnier to show a follow-up article from, I think, a month later, or even less than a month later. This is from Tuesday, November 27th, 1979, front page of the science section. And it was about Khachiyan himself. Soviet mathematician is obscure no more, it says. And yeah, that's the top story, plus ça change. Yeah, but about Khachiyan, I just think it's funny, it starts out by talking about the mystery author of a new mathematical theorem, and the dark-haired bachelor says he was somewhat surprised by the enthusiastic response and so forth. And it ends by, this is the end of the article, and says, his absorption in his work appears to be total. I tried to take up karate as a hobby about 3 years ago, he said, but now I do mathematics instead. So good times, yeah. There's another follow-up article from New York Times. And it's also, when, Khachiyan showed his linear programming was in P, it made the front page of The Guardian and Der Spiegel. So it's really big news. So I'm, happy to tell you about it today. Actually, probably Khachiyan's daughter is more famous than Khachiyan himself right now. You can follow her on Twitter. She's got 46,000 followers. Okay, but enough history lessons. Let's go back to the math. So here's the linear programming problem again. And actually, what I want to actually talk about today, we won't talk about the polynomial time algorithm yet, but we're going to talk about sort of the theory of it and why it's possible that you can solve it in polynomial time. In the next lecture on Thursday, we're actually going to talk about applications of linear programming in combinatorial optimization, but today will be about sort of the theory of linear programming. And let's actually, one way we're, oops, I wanted to say something about that. the fact that this problem is solvable, the fact that when k is empty, you can find a point x in polynomial time, one interesting thing that implies is that a solution, if it exists, can be written down with polynomially many bits. And that's actually not obvious. So that's interesting. We'll get into that. And, on the other side, what if k is the empty set? Well, we'll think about that too. So let's now sort of dive into this question about what is meant by a proof that a system of linear inequations cannot be satisfied, or what would like a proof or a certificate that an algorithm might output look like? Okay. Any questions? Okay. Well, maybe it's easiest if you type them in the chat, and I'll keep an eye on the chat window as we go. Okay, right, so what does it mean by a proof or a certificate that a system of linear inequations like this has no solution? Well, suppose this was your input instance, and I suppose I just told you, hey, add up all these inequalities. If there's a solution to all these inequalities, then that solution x should also satisfy the sum of the inequalities. And imagine, like, by some weird miracle, when you just formally add up the left-hand sides, like all the coefficient sums add up to 0, the left-hand side cancels out completely. You get 0 on the left-hand side, and the right-hand side adds up to like the number 1 or some other positive number. Okay, then that would show that no matter what x is, if it satisfies all these inequalities, it would also satisfy their sum. And in this miraculous setting, the sum is 0 greater than or equal to 1, which is, not true. And that would be a proof, or that would be like a demonstration that these inequalities have no solution. You can generalize this a bit. More generally, if you have an inequality, you can always multiply it by a non-negative number lambda, and it'll remain equivalent. And suppose I pointed out some non-negative multipliers, lambda 1 through lambda m, and you multiply the inequalities up with these numbers, lambda 1 through lambda m, and added them up. And then the miraculous thing happened, which maybe is less miraculous if you choose these lambdas carefully, that everything on the left-hand side cancels out, and everything on the right-hand side becomes the constant 1. Okay, this would be also demonstrating that there's no solution to these inequalities. And this is the kind of proof of unsatisfiability that we're going to be talking about for linear programs. Right, so you'll multiply each of these inequalities by lambdas that are non-negative, and then you'll add them all up, and all the coefficients will come out to 0 on the left-hand side, and on the right-hand side, you'll get the number 1. So let me do something here. Okay. Great. So if such lambdas existed whenever the system was unsatisfiable, then it would mean you have like a cool, succinct way to prove that unsatisfiable systems are unsatisfiable. And this always happens. And this is the content of what's called the Farkas Lemma, or it's basically the same thing as LP duality. And it's this theorem, which I'll show to you, that whenever a list of inequations has no solution, so the k that they define is the empty set, there is a proof of this sort. These non-negative lambdas, which when you multiply them against the inequations and add them up, they give 0 greater than or equal to 1. Such lambdas always exist. Okay, and this is proved by Farkas in 1898, basically also proved by Gärtner in 1873, but somehow he never gets the credit. He's actually probably most famous for being Emmy Noether's PhD advisor these days. Okay, I'm getting a question here. Let me check it out on chat. The question is, does that mean that if all the coefficients on x1 were positive, it's always satisfiable? Yeah, that's exactly true. So it is true that if all these coefficients on x1 are positive, then it's always satisfiable. And the reason is, you have a solution where you just set, let's say, x2 through xn all to 0, and then set x1 to be some enormous number, positive number, big enough so that it would exceed all the right-hand sides b1 through bm. Okay, so this relies on the fact that our inequations are all of this form. They all have greater than or equal to signs. Does that make sense? Okay, good. Cool. Good question. All right. And this also, by the way, this was known in like the 50s and stuff and 40s. And basically, if you ignore these things about bit complexity, it tells you that, obviously, if a list of inequations has a solution, then you can just show the solution x, and so that proves that linear programming is an NP. And this also, Farkas Lemma also implies that when there is no solution, you can just show these lambdas, and it's sort of a witness or certificate that there is no solution. So people knew all along that linear programming was in NP intersect co-NP, if you remember this complexity theory stuff. And that kind of hinted that it was perhaps just in polynomial time solvable in P, which indeed proved to be true. Okay, so I'm going to show you a proof of the Farkas Lemma. It's sort of a proof by example. And the proof uses this thing called the Fourier-Motzkin elimination algorithm, which in a sense is an algorithm for solving linear programming, but as we'll see, it's like an extremely inefficient algorithm, but it's an algorithm that is useful for theoretical reasoning. Good. So let's suppose this is your input. There's just 3 variables here. So instead of x1, x2, x3, I'll call them x, y, and z. And so you have these 5 inequalities. Okay, and we're going to try to reason about whether or not they're simultaneously satisfiable. So just like you're taught in high school or whenever to solve systems of linear equations by this technique of first eliminate the first variable, then eliminate the second variable, then eliminate the third variable. You can also do that with linear inequalities, and that's what Fourier-Motzkin elimination does. So the step 1 is to somehow take this system of linear inequations and find another system that doesn't involve x at all and whose satisfiability status is the same as the satisfiability status of the original system. So how are you going to eliminate x? So let me tell you. First thing you do is you multiply all the inequalities by positive constants, so as to make the coefficient in front of x either +1 or -1. Okay, so whenever x had a +1 or a positive coefficient before, it's going to have a +1 coefficient here on the new set. And whenever it had a -1 coefficient before, or sorry, a negative coefficient before, it's going to have a negative 1 coefficient on x in the new set. Okay, so that's easy, and it doesn't change the set of solutions, in fact. Now, don't change the inequations at all yet, but mentally think of them as being upper bounds and lower bounds on x. So whenever you have like a positive x, you can think of this as an equation on the left here that's like x is bigger than some stuff involving y and z and constants. And whenever you have an equation whose coefficient on the right is minus, you have minus x, you can think of this, if you move the minus x to the other side and the constant to the left side, you can think of this as an inequation of the form x is less than or equal to some stuff. Great. So, and if you have some inequality in the right system here that doesn't involve x, just like temporarily forget about it for a moment. So we'll just think about what bounds are implied for x here. And now you see it's not too hard to understand. You have some expressions that x is supposed to be bigger than and some expressions that x are supposed to be smaller than. And like, think of y and z. I just put the original system back up there. Think of y and z as numbers. Temporarily think of y and z as numbers, but x is like a variable. And then over here, your constraints on x are then x is bigger than some numbers and x is smaller than some numbers. And you see, there is a legal or an acceptable solution for just the variable x, if and only if all the lower bound numbers are smaller than or equal to all the upper bound numbers. Right, so this thing involving x over here on the left is satisfiable or has a satisfying x if and only if all the lower bounds are smaller than the upper bounds. So we can just kind of take a cross product here of all possible pairs of a lower bound and an upper bound and make a new inequation about it. Okay, so we have the red lower bounds or reddish lower bounds and the greenish upper bounds, and we'll sort of take this cross product. So this is actually going to make a lot of inequations as we do this, but as I mentioned, this algorithm is not efficient. And on the right now here, we have 4 inequations which are satisfiable if and only if this set on the left for a given y and z, they're satisfiable or satisfied if and only if for this guy on the left there exists a satisfying x. Does this make sense? So this is what I said. There's a satisfying x on the left if and only if we have all these upper and lower bounds square with each other. And let me just take them and simplify them, collect all the terms. So I've done that here. You can take my word for it. And now we can just remember the original system we were thinking about. We also had this one inequation that didn't involve x at all. So let's stick it back in. And we've actually done it. We've actually shown that this initial system with the x's is going to be satisfiable if and only if this new system with no x is satisfiable. Okay, so we've successfully eliminated x. Okay, any questions about this? Okay, great. Okay, so obviously the next step is to eliminate y. And I won't go through that whole process again, but I did it. I probably made some numerical errors, but I believe when you eliminate y in this specific example, you get down to just a bunch of inequalities that only involve z. And actually, when you're down to one variable, it's easy to check if it's satisfiable or not, but we can even go like the whole Megillah and eliminate z itself. Eliminate the last variable. And when you do that, you get down to just a bunch of inequalities involving numbers, okay? And then it's really easy to check if they're satisfiable or not. You just check, hey, are all the right-hand sides negative? And actually, in this case, they're not. And that implies that the original system was not satisfiable. Okay, but on the other hand, if all the right-hand sides were negative, then that would imply that the original system was satisfiable. So what I've shown you here is a highly inefficient algorithm for deciding the linear programming problem. There's a certificate right there. Well, this is a witness that it's unsatisfiable. Let me also just mention that you can always multiply an inequality by a non-negative number, and it preserves the inequality. So you can always get your final, unsatisfiable equation to be 0 greater than or equal to 1 if you'd like. And now I want to make a key claim. What I want to claim is that every inequality that you generate in this whole Fourier-Motzkin elimination algorithm is a non-negative combination of the original inequalities. And in particular, if that's true, then it means even this last one, in the unsatisfiable case, even this last one, 0 greater than or equal to 1, is a non-negative combination of the original inequalities. And that actually is going to prove the Farkas Lemma, right? That's what we're trying to show. When it's unsatisfiable, there's some way to add up the original inequalities with non-negative multipliers to get the blatant contradiction 0 is greater than or equal to 1. And let me just illustrate this claim for you. Well, I mean, I'll kind of go over the steps quite fast. Here was the original system on the left. The first thing we did was multiply the inequalities by positive constants to get like all plus or minus 1 coefficients on x. So that's multiplying them by just non-negative coefficients. And then we eliminated x. And if you think about it, this is the previous version with x. This is the version with x eliminated. And if you think about it, actually, we got all these first 4 inequations here involving y and z by taking just pairwise sums of the plus x inequations and the minus x inequations on the left. Okay, so for example, we got this first one involving y and z by just summing the first inequation with a plus 1 on x and the first inequation with a minus 1 on x. Okay, so that indeed demonstrates that after this elimination step, all the inequations here indeed were non-negative combinations of original inequations. Okay, and then, in the next step, when we eliminate y and get down to z's, just z's, all those just z's inequalities will, be non-negative linear combinations of these inequations here on the right, which in turn were non-negative inequation or multiples of these inequations involving x, y, and z in the original case. So all in all, as you go along, you maintain this invariant that everything is a non-negative linear combination of the original inequations. Okay, does that make sense? Any questions? Okay. Great. So that, in a nutshell, proves this Farkas lemma, or this LP duality statement. Now, let's make some more observations. Let's go back to this Fourier-Motzkin elimination algorithm. Just think about it a little bit more. In fact, I told you this was a good thing to think about when you're trying to reason about what happens when the system is unsatisfiable. You'll eventually be able to make 0 greater than or equal to 1 as the linear combination. But actually, if it is satisfiable, and in the final step you get all down to 0 greater than or equal to some negative numbers, it's an easy exercise to show that actually you can now sort of go back one variable at a time and reconstruct a solution, and in fact a rational solution, because I don't know, for example, let's say you've inductively done this so far and you have some solution for y and z, and now you just need to figure out how to set x such that all these inequations on the left are satisfied. Well, the way it's set up, right, with these y and z now being numbers, the whole point is that and being satisfiable means there is a value of x which is between all the upper bounds and the lower bounds. So you can just choose any x that's between these upper bounds and the lower bounds that you've worked out, and that'll be an acceptable setting for the variable x. Okay, so you can inductively build back a solution from the eliminated variables one by one. In particular, that shows that if you start out with rational coefficients, which we always assume, then you can actually get back a rational solution. Okay, so it's a minor comment that there's always a rational solution. Now, as I said, this is a highly inefficient algorithm. It's not the polynomial time algorithm for linear programming. And in particular, you can see if you start out with, like, let's say m inequalities, you're doing this elimination step, maybe half of them have a positive coefficient and half of them have a negative coefficient. You take like the cross product between them, you'll generate m/2 squared inequalities. So even eliminating one variable kind of squares the number of inequalities you have. So if you eliminate n variables, you get a doubly exponential time algorithm, like m to the 2 to the n, okay? Which is, of course, very bad. But we learned some things by thinking about it. We learned the Farkas Lemma. We learned there's always a rational solution when there is a solution. So it's still worth thinking about. Right, so is there a polynomial time algorithm for linear programming? Well, there is, as I mentioned, but we'll get to there in the end after actually maybe 2 lectures from now. But before getting there, we should actually, again, come back to this sort of technical but interesting to me question. Before wondering if there is a polynomial time algorithm, we need to wonder if there are even polynomial bit solutions. Okay, so remember, a solution, when it is feasible, when k is feasible or non-empty, you're looking to find a quote-unquote feasible x, meaning an x that satisfies all the inequalities, or else you want lambdas which prove that x equals the empty set. And here, what do I mean by bit size? Well, remember, we're working with digital computers and, either the word RAM or the Turing machine model, but in any case, every number, you can't work with it by magic. You have to store it, and it's going to be a rational number. So I'm going to use this notation just in this lecture because it's traditional. The bit size of an object, I put in angle brackets, and it's the number of bits needed to encode it in like a standard method. Okay, so for an integer, it's the number of, base 2 digits of x. And if it's a rational number, we're just going to store it as like a numerator integer and a denominator integer. If it's a vector, then it just means, the sum of the encoding lengths of all the numbers in the vector, same as if it's a matrix, et cetera, et cetera. And an important theorem for linear programming, which is sort of necessary in order to show that there's a polynomial time algorithm for linear programming, is to show that the output that you're looking for, the feasible x, if it is satisfiable, and the proof of infeasibility, if it's not satisfiable, can be written down with polynomially many bits. So luckily, that's true. So here's a theorem that we're going to reason about. It says, let's say you're given a system of inequalities k, and it's traditional in linear programming to write capital L for the number of bits needed to encode k. So there's a number that's like m plus n plus the encoding length of all the numbers in the inequalities. That's L. And it says you're in good shape. So if k is non-empty, there is at least one solution. Then not only is there a rational solution, x, but there's one that you can write down with poly n bits. And if k is the empty set, then there exists a rational proof of these lambdas that also have only polynomial in L many bits. And what is the proof of this? Well, that's what I want to talk about for a little while. First thing I'll say is actually it suffices to show bullet point 1. It suffices to show that when there is a solution, there's a solution with polynomially many bits in it. And what is the reason for this? Well, if we suppose we knew it was true for bullet point 1, how could we reason about polynomial bit size for the lambdas in the case where it's unsatisfiable? Well, and this is a bit of a detour, but the reason is, once you know it's unsatisfiable, or when you're interested in this, the question of given k, are there lambdas which certify that k is unsatisfiable? This itself is a linear programming problem in the variables lambda. So I'll talk about why that's the case in a moment. But this is called the dual linear program. And this dual linear program in the lambdas, its bit size is about the same as the bit size of your actual system k. And so this is why it suffices to show bullet point number 1, assuming this fact about there being a linear program for the existence of the lambdas. To get bullet point 2, well, you just use bullet point 1, but applied to the dual linear program about the lambdas, whose bit size is about the same. It's also about L. Okay, so yeah, why is this question of finding the lambdas certifying unsatisfiability of k, why is it itself a linear program? Well, let's just look back at the Farkas Lemma, which is here. This is our input data, these inequations involving the x's and the a's. And the Farkas Lemma says that if k is the empty set, if these are unsatisfiable, there are these non-negative lambdas, which when you multiply them against the inequalities and add everything up, you get 0 greater than or equal to 1. So let's just rearrange this a bit. We're looking for lambdas which are non-negative, which is a good start, right? You're allowed to have these as constraints in a linear program. Think of now the lambdas as the variables, and the x's are kind of going to go away, and the a's are going to remain constants, and the b's are going to remain constants. So yeah, so now if you think about this a little bit more, to say that, let me go back a little bit, to say that the lambdas, when you multiply them against the inequalities and add them up, to say that you get a coefficient of 0 on x1, it's just to say that lambda 1 a11 plus lambda 2 a21 plus dot 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 lambda m plus am1 is equal to 0. And that's encoded by this vector matrix multiplication. That first constraint is saying that this row vector of lambdas times this column vector of a's equals 0. And we want a similar thing for all of the columns. We want the row vector of lambdas times the second column of a's to equal 0, dotted with, I should say. And it should be true for all of the columns. They should equal 0. And then we also want that the dot product of the lambdas with the b's should equal the number 1. So really what we've got here is a bunch of equations on the variables lambda, plus the constraints that the lambdas be non-negative. And this is indeed a valid linear program. And this program is the dual linear program. It's the one about certifying unsatisfiability of the original k. Any questions about this? Okay. Good. So, good. So as I said, this means for our theorem here about bit sizes, it suffices to show this, statement number 1, that when you have a system of inequations and the bit size is L, takes L bits to write down your input, then assuming there is a solution, there's a rational solution that can also be written down with poly-L many bits. Okay, so let's think about how to prove this. Try to draw a picture here. This is Rn. Well, I guess n is kind of like 2 on my slides, but it's like Rn. And here we have like 3 inequalities depicted, and their intersection is non-empty. It's this triangle K. Okay, so the first thing that I want to claim is that when K is not the empty set, so there are at least, there's at least one point inside K, then there's always a feasible, not just a feasible point X inside, but a feasible vertex, which I'll call X star. And what is a vertex? It's like a corner. So this is an example. It's, one of these corners. If K is like a polytope, it's like a vertex. It's like a corner of the polytope. And this is actually not true due to like a little annoyance, but we'll come back to this stupid annoyance later. So just for a moment, prove that this is, assume this is true, because it's true in essentially all cases, or in the nice case. Okay, and these vertices, which are also called extreme points or basic feasible solutions, are very important in the theory of linear programming, which is why I guess they have a threefold synonyms here: vertex, extreme point, basic feasible solution. These are all kind of the same thing. And in fact, we're going to reason about not only will there exist, you know, a solution X with polynomial bit size, but actually one of these vertices, in fact, all of the vertices of all the corners will have polynomial bit size needed to write them down. So what is a vertex? Remember in this picture, right, you have a bunch of m linear inequations in your initial k. And if you turn the inequalities into equalities, then you get like a half space. These are sort of depicted by these white lines over here in the diagram. These are half spaces, and the inequalities are the half spaces. And we're in n dimensions. So a vertex is really, what it means is it's the unique solution of some n linearly independent half space equation. So if you think of like an inequality as an equation in your mind and view that as defining a half space, or like, yeah, an equality, you know, we kind of know, unless modulo annoyances, if you have n equations in n unknowns, then there's modulo annoyances, you know, a unique solution. It's true when they're linearly independent. And these are affine half spaces, by the way, and meaning they don't necessarily go through the origin. There's a non-zero right-hand side. And these solutions are these vertices, like the corners of K. Okay, so in this picture where n is 2, these yellow lines, which are your half spaces, they intersect here. Two lines, in 2 dimensions, they intersect at this vertex of K. And therefore, it means that this vertex here, or any vertex, x star, is the solution to an n by n system of equations, like a subsystem of the m inequations that you're given. You view them as equations, and then the vertices, like this vertex, is the solution to an n by n system of equations. And this means that the solution, this vertex x star, can be written down with polynomial in L, you know, many bits. And the reason for that is basically because, you know, solving systems of equations is a polynomial time algorithm. You know, we have Gaussian elimination. You take some rational system of equations and variables and knowns. Any such a system that defines a vertex, you solve it, and you get a vertex. And, you know, since it's a polynomial time algorithm, you only have time to output polynomially many bits, which means that x star, the vertex, can be written down with polynomially many bits. I still have this quotation marks here, but we'll come back to that in a moment. Actually, I just want to mention that I'm a little bit eliding some complications here, because in fact, the fact that Gaussian elimination is in polynomial time is a pretty non-trivial fact. It's proven by Edmonds in 1967, and it needs a little bit of sophistication. It needs Cramer's rule. So the algorithm you remember from linear algebra class, it, you know, takes polynomial steps in n, if you're solving an n by n system for sure, n cubed steps maybe. I have a question here. The question is, what is Gaussian elimination? Gaussian elimination is the, you know, classic algorithm that you learn in linear algebra class for solving like an n by n system of equations. Usually you kind of just, Gaussian elimination refers to the algorithm you take like the matrix for the equations, and you kind of, it's kind of similar to Fourier-Motzkin, like you kind of clear out, you know, a whole column, you try to eliminate the first variable, and eliminate the second variable, and so forth. So basically, it's the algorithm you learn for solving systems of equations. And yeah, this, as I said, this, you know, involves n squared or n cubed steps or something. But the thing that's annoying is checking, you know, these rational numbers that you generate as you go along, that they don't, you know, blow up and require exponentially many bits to write down the numbers that are generated. But it's true. And perhaps you'll see that on the homework. So let's just take that for a given, that if I give you a system of n variables, n unknowns, all the coefficients are rational. You can solve it in polynomial time, and so the answer is polynomially many bits to write down. Okay, any further questions about this? Does it make sense? Okay. So what's this annoyance that we need to come back to? Well, the annoyance is that sometimes there are no vertices. So here's a perfectly valid linear program. N is 2, m, the number of inequations, is 1. It's just like x1 plus x2 is greater than or equal to 1. You have 1 half space. Here's the feasible region. It's everything above, to the northeast of that. And there's no vertices. It's just a line. So that's a problem. If you have vertices, if K has at least one vertex, then you can conclude that it has, this vertex can be written down with polynomially many bits, and you can conclude that there's a polynomial size solution. You could have these like terrible LPs with no vertices, but the only way this can happen is if like they're unbounded, which is a perfectly normal thing that can happen, but we want to get around this. So the preceding proof would be fine about vertices and so forth if K always included what I call big box constraints. This is not a real term, but it's just a term I made up for this lecture. What are big box constraints? I say you have quote unquote big box constraints if your linear program, your set of inequations, also includes for every variable xi a two-sided equation saying xi is between negative b and b, where b is like some really big number. Okay, it's like saying, oh, my linear program is k, but plus like I only want to worry about x's that are inside a gigantic cube of side length 2b. Okay, and b, the kind of b's I'm going to be thinking about are ones whose representation size is polynomial in L. But remember, that means that b itself, like if b is an integer, its actual magnitude is 2 to the poly L. But that's okay because you write it down in base 2, so the number of bits needed to represent it is poly L. So we're going to like it if you have big box constraints, because if you have big box constraints, then like this, then even if your original K were like unbounded in some directions, the fact that you have a big box forces the intersection of K and this big box to have some vertices. Okay, so what I want to show is basically whenever you have a linear program K with bit complexity L, you can sort of, without loss of generality, put in big box constraints for a big value B that takes polynomial in L many bits to write down. Okay, and once we show that, then all this argumentation about there exists a vertex is true, and therefore there exists a rational solution that takes polynomially many bits to write down is true. Okay, does that make sense? Any questions? Whoops. Okay. Great. Okay. And yeah, what's nice about this is these always give you n linearly independent equations. If you can imagine converting them into equations, they just look like xi equals b and xi equals negative b. You have one for each variable, so it's kind of like you have n linear independent equations, which is another reason you'll be able to find n linear independent equations making a vertex. Now, I want to show you that you can always add these big box constraints, and it almost seems like I'm making like a circular argument here because, this is sort of what we were trying to reason about in the first place, that we were trying to reason that you could a priori sort of only worry about numbers that are at most polynomially many bits large. But, I'm going to show you how to make it non-circular. So in order to do this, I have to talk about converting a linear program of the type we've been interested in before, just with all inequations like this, which is called standard form linear program, to an equivalent program in what's called equational form. And an LP is said to be an equational form if there are basically no inequalities, you only have equalities. Well, that can't quite be right because, I mean, then it would just be a linear system of equations. But you have all variables constrained to be non-negative. So equational form is a special kind of LP where you have only equalities, but you insist that all the variables be non-negative. And what I'm going to show you now is that given any standard form LP, you can convert it into an equivalent equational form LP. Okay, where it's like easy to go back, so they have the same satisfiability status, and it's easy to go back and forth between a solution for one and a solution for the other. Okay, so how are we going to do this? This is just some simple tricks for converting this to an equational form. So trick number one is in K, the xi's, the variables, are not constrained to be non-negative, but they're supposed to be in this final version K prime. The xi's are not constrained at all per se. They're just involved in the inequations. But this is no problem. The trick here is the following. You take each variable xi and you replace it with two variables called xi plus and xi minus. Well, you don't replace it with that. You introduce two new variables, xi positive, xi negative, and you replace xi with their difference. And you see if you plug, this into some inequations, it turns one inequation into another inequation, just in twice as many variables. And you are going to constrain xi plus and xi minus to be non-negative in your final K prime as needed. And this is why it's valid. It's just valid because any real number can be written as a difference of two non-negative real numbers. Regardless of whether the initial real number is positive or negative or zero, you can always write it as the difference of two non-negative numbers. And conversely, the difference of two non-negative numbers has no particular constraint on its sign. So this is a valid move. Oops, okay, so good. So that takes care of this aspect. The other problem, besides the variables not constrained to be non-negative, is that your constraints are inequations and they're supposed to be equalities. Okay, and the way to get around this is also pretty easy. You take each inequation like this, like this a dot x is greater than or equal to 0, and you replace it with a dot x minus b equals s. And this s is called a slack variable. It's a new variable that you introduce. And, we see it has to be constrained to be non-negative. So indeed, SI is constrained to be non-negative. And now, but you see that this equation with the new slack variable, you have one of these for each original inequality. This new equation, together with the constraint that the slack variable is non-negative, is equivalent to the original inequality that said, a dot x is at least b. It's the same as saying a dot x minus b is non-negative. Good. So if you put these two fixes together, it does the job. It converts this k that has only inequalities to this k prime that has only equalities, but with all the variables non-negative, constrained to be non-negative. Any questions about this? Okay. Okay. Good. So let's go back here. Right. So what I've told you now is that we can take any standard form LPK and convert it to an equational form LP that's equivalent. And let's write this equational form LP in a bit of a simpler form. Let me just also remark that you can obtain K prime efficiently from K, and the number of K prime is very similar to K. So the number of bits you need to write down K prime is probably linear in the number of bits you need to write down K. They're polynomially related. Okay, so we can, when we're given K, remember, what are we working towards here? We're working towards trying to show that given any feasible LP, or even infeasible LP, any LP, you can sort of, without loss of generality, put in these big box constraints without affecting satisfiability. And what I'm just showing you here is, given K, you can just convert it to equational form and think about that. Okay, so let's write K prime a little bit more briefly. So x's, we're going to call the variables x now, even though really they're, it's like the xi plus and minus and also the s's, but I'm going to kind of forget all that and just say, okay, let's just call the new variables x and the new b is b. And so, yeah, an equational form LP looks like this. It looks like A is a matrix here, so it looks like AX equals B. That's your bunch of equations. And x greater than or equal to 0. And this is a shorthand for the coordinate-wise statement that each of the components of x, x1 through xn, is greater than or equal to 0. we're going to continue again to call the number of variables n and the number of constraints m, even though it actually changes a little bit when you go from standard form to equational form. Okay, so let me simplify this a bit more. Okay, and now once you get to equational form, or once you have an LP in equational form, you can make a few other simplifications or a little observation. So let's say A is m by n. There's n variables and m constraints. And another thing you can assume without loss of generality is that A has full rank. So if you remember your linear algebra, what does this mean? It means each equation is linearly, the equations are linearly independent of one another. No equation is, a linear combination of other equations. Like no equation is automatically implied by other equations. So all the equations, are linearly independent. They stand on their own. And this is without loss of generality, because if you have some like redundant equations or equations that are applied by other equations, you can just eliminate them from K prime and it won't change K prime's nature. So we can assume without loss of generality, and an algorithm can actually algorithmically do this efficiently if it wants, again, by basic linear algebra stuff, Gaussian elimination again, in fact, or row reduction type stuff. So we can assume that A has full rank, and so actually the number of rows of A will be less than or equal to the number of variables. Okay, you'll have n variables, and you'll have either 1, 2, 3, 4, 5, ... n equations for some value m between 1 and n. And so this AX equals B, this is like a subspace. It's an affine subspace. And K prime is saying, K prime is like everything that's on this subspace. I'll draw a picture in a second, where all the coordinates are non-negative. Okay, so I'll draw a picture in a second, but now let me just say, I want to show that once we're in this equational form like this, whenever, K prime has a solution, it has a solution where the bit complexity is not too big, and therefore we can equivalently add these big box constraints. Okay, so here's a picture. I'm going to try to draw a picture when n is 3. And right, so in K prime, you have this non-negativity constraint. So all your solutions should be lying in this non-negative orthant. I don't know if it's supposed to be, you're supposed to imagine that like you're sort of looking at the origin, the non-negative orthant is like close to your face. Okay, and then what the picture looks like depends on what m is, like the number of equations involved in K prime. So let's imagine case 1 that m equals n. So you have like n equations and n unknowns, and they're linearly independent. Okay, in that case, K prime is just a point. It's the solution to the n equations. And K prime being feasible, or satisfiable, simply means that this point is in the non-negative orthant. Like all its coordinates are non-negative. So you're right, this point is just the solution to AX equals B in this case. And, just for these reasons we talked about, since solving a system of equations can be done in polynomial time, the solution to a system of linear equations can be written down with polynomially many bits. So in this case, where your equational form solution has m equals n, your solution will have polynomially many bits. And therefore, it's okay to take, B to be a number that's a bit, that also can be written with polynomially many bits, like an integer that's like a bit bigger than the maximum possible solution to a system of equations in your LP is. Okay, does that make sense? So I want to argue that like if you have an LP in equational form, maybe you've converted to an equational form, and you got rid of the redundant equalities. If you have n equalities, then the solution, provided it exists, is inside a big box, but not too big. One that can be written, where the side length can be written with polynomially many bits. Okay, so case 2, what if m is n minus 1? Well, in that case, you have n minus 1 equations and n unknowns. The solution to that is a line. It's like an infinite line. And then K prime is like the intersection of this infinite line with the non-negative orthant, which, the line might or might not pass through the non-negative orthant. That's the question of whether K prime is satisfiable or not. It has a solution or not. But if it does, then the picture sort of looks like this. If you can try to imagine what I'm drawing here, it's like a line piercing the non-negative orthant and making like a line segment. It'll at least be a half-infinite segment, if not a finite segment. What I want to argue is it has to hit at least one of the coordinate planes, the 3 coordinate planes, x1 equals 0, x2 equals 0, x3 equals 0. You can imagine if this line is exactly parallel to one of the axes, like it might hit only one coordinate plane, assuming it does hit the non-negative orthant. But there's no way like it can hit the orthant yet like miss all the coordinate planes. So what I'm arguing there is the algorithm doesn't have to know this or anything. An algorithm doesn't have to know this. But whenever you have a feasible K prime like this, where m is n-1, so you have this line that does pierce the non-negative orthant, it has to hit at least one coordinate plane. And therefore, there exists some equation like xi equals 0 that you can throw in, hypothetically, without changing satisfiability. But once you've done that, you've reduced the case of m equals n. Okay, and the solution is just a point. It's the solution to the whole system of equations together with this new xi equals 0. So again, yada, 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 the solution with this xi equals 0 will be expressible with polynomially many bits, and the big box thing is okay. Okay, and this generalizes. So if m is n-2, then k prime is the solution to n-2 equations and n unknowns. It's like a two-dimensional flat intersected with the non-negative orthant. And again, there's no way it can hit the non-negative orthant without hitting at least one of these coordinate planes, xi equals 0. And therefore, again, you can throw in at least some equation of the form xi equals 0, which gives you like a new equation, and it reduces m to n-1. And then you can like inductively argue that you can reduce from n-1 to m, et cetera, et cetera. And so, yeah, what I'm trying to say is no matter what actually m is, whatever the rank is, if there's a solution, then there's some fixed b, integer b, with polynomially many bits that you can write down, bigger than any output of Gaussian elimination or a linear system solver. That's sure to include at least one feasible point. Okay, so the summary is, given a system of inequalities k with bit size L, its feasibility is unchanged if you add these big box constraints, where b has polynomially many bits. I think even quadratically many bits is sufficient. And this even, now we've proved it when the LP is in equational form, but it follows kind of immediately. You just think about how equational form and standard form are equivalent, but it's also true for the original standard form, that you can put in these big box constraints without changing satisfiability. Okay, and in light of this, what we can conclude is that when k, given LP without these big box constraints, k is given if it has a solution that in fact has a vertex solution, and this vertex can be written down in polynomial size. And if it's empty, there's a proof lambda in the dual, and the proof can also be written down with polynomially many bits. Okay, and this actually formally shows that linear programming is in NP intersect co-NP, if you remember your complexity theory. Any case, I mean, as we all know, and we will show later in this class, it's in fact in P, but now we're sort of fully warmed up to the fact that it has the potential to be solvable truly in polynomial time. Any questions right now? Okay. Good. So, in the last part of the lecture, we're going to talk about moving from, well, the decision problem that we've been talking about so far, whether or not a given system of linear equation inequalities K has a solution or not, to the more familiar problems like, if I give you a system of linear inequalities and you figure out that it does have a solution, like how about finding a solution? So far, what we're going to show actually in a couple of lectures is that there is an algorithm, the ellipsoid algorithm, Kachian adapted for linear programming, that can solve this decision problem. Given K, is it feasible or not? But now, in the remainder of the lecture, I'd like to talk about, well, what about the search problem? Like when K is feasible, can we find a point X in the polytope? And probably the most familiar aspect of linear programming is the optimization version. And that's where, under the assumption that K is non-empty, you also have like an objective function, which is a linear function of the x's, like c dot x, like c1 x1 plus dot 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 cn xn, that you want to maximize. So linear programming is usually thought about like this, like you're given the inequalities, you want to find a point x that satisfies all the inequalities while maximizing this linear expression c dot x. And what I'm going to tell you in the remainder of the lecture oh, I should also mention I said maximizing here, but you can also equivalently do minimizing, because if you want to know how to maximize c dot x, it's the same as minimizing negative c dot x. Okay, so what I want to tell you in the remainder of the lecture is that you can get from just the emptiness decision problem to these more complicated problems using polynomial time reductions. So the way it's typically formulated is like this. Let's imagine that we have a quote unquote oracle for solving this feasibility decision problem. You know, we have some magical oracle that can, given a set of inequalities, K, it'll correctly tell you yes or no. I suppose this is a bit wrong. The feasibility question is whether K does not equal the empty set or not. So it'll tell you, you know, does K contain at least one point or not? Okay, and eventually we'll implement this oracle. The ellipsoid algorithm will let us show that, you know, there is a polynomial time algorithm for this. But let's assume now that we have this algorithm, and we're going to I'll show you now how you can use it to solve the search problem and the optimization problem using sort of like black box use of this oracle. Okay, so that, you know, once we get this oracle for solving the feasibility problem, we'll have everything that we'll want to have. And we'll be able to move on to the glorious, you know, algorithmic applications of having this efficient algorithm for linear programming. Okay, so let's start with the search problem, assuming we have a feasibility oracle. Okay, so the thing to have in mind is we have some magic box that can tell us if a system of inequations has a solution or not. And now we have some actual system of equations, you know, K, that we care about. And maybe we use the box one time and the box says, yep, it has a solution. And you're like, great, now I would like to actually find a solution. So how can we do that? Okay, well, the first thing we can do is put K into equational form. We saw that was without loss of generality. And I also mentioned that, like, if you have some K not in equational form, you put it into equational form, you find a solution to the equational form, it's easy to transform it back into a solution to the, like, standard form. I mean, really, you can just disregard the slack variables, and you have these xi pluses and xi minuses, and then to get xi, you just subtract them. Okay, so we can assume that K is in an equational form, which is like sort of the nice form for all this reasoning. And so we think of K as looking like this again: ax equals b, x is constrained to be non-negative, and A is some m by n matrix. We assume it's full rank, so it has no like redundant equations, and the number of irredundant equations is m. That's at most n. In this picture, like again, n is 3. Maybe m is 1 in this case. We have this two-dimensional hyperplane. And K is like everything in this two-dimensional hyperplane that intersects the non-negative orthant. Okay. And, you know, we can call the feasibility oracle once and find out that this K has a solution. So now we kind of know that this two-dimensional hyperplane does have at least one point in it that has all non-negative coordinates. But now we'd like to find such a point. So, you know, a typical scenario is maybe m is like, I don't know, n over 2. Okay, it's neither particularly close to n nor particularly close to 0. Just imagine that we set everything up and m is like half n. So again, by this reasoning we talked about before, right, if K is feasible, then not only does it have to pierce the non-negative orthant, it has to hit at least one coordinate plane, xi equals 0. Okay, I mean, it could be parallel to a coordinate plane, but it cannot be simultaneously parallel to all of them. So there must exist a coordinate plane, xi equals 0, which is consistent with K. I mean, you intersect K with this coordinate plane, and you still get a non-empty K. Now, the point is, you can use your oracle to find such an I. Okay, so you can just use the oracle n times, take K together with, you know, x1 equals 0, and ask the oracle, hey, is this feasible or not? Yes, no. And if it says no, then try throwing in x2 equals 0 instead. Is this feasible? Yes, no. Maybe no. Maybe K is parallel to the first coordinate plane and the second coordinate plane. But you can do this, you know, n times, which is fine. And at least one time you'll have to get a yes answer. Okay, and once you get the yes answer, you're like, great, now I know that it's consistent with K to throw in this xi equals 0 that I found. You throw it in there, you've reduced, now you've got one more equation. So you sort of reduce the m equals n over 2 plus 1 case, and then you can repeat. You just repeat, find like a coordinate plane that you can consistently throw in. And finally, you'll get down to m equals n. You'll have a system of linear equations, and you've maintained that like it's always like a subset of K. it's always in the non-negative orthant, and it's feasible. So then you just solve that system of equations, and you've found your x. Okay. And one thing that I was actually confused about myself when I was making this slides, I was thinking, you know, I mean, why do I really need the oracle? Like, this kind of gives me a recursive algorithm, given the initial k, for like finding a solution. Just try the n possible xi's, and then, you know, recurse. But why do you need the oracle? Like, why is this not a polynomial time algorithm? Well, it's simply because, you know, this recursive algorithm, it has like branching factor n, and there's potentially n depth. So if you just try to execute this algorithm without the oracle, you can do it, but it'll take you like n to the n time, because you really have to recursively try all the xi's. But with the oracle, you don't have to try all the xi's. Well, you try them once, but like, you know which is like a successful branch to recurse down. Okay, so you only have to make n squared oracle calls here, you know, one for each level, to successfully narrow in, zoom in on the xi equals zeros that are consistent. Does that make sense? Why is it not n to the n instead of 2 to the n is a question. Is it 2 to the n? I was just thinking, okay, like there's a branching factor of n, and you have to do it like up to n times, that's n to the n. Maybe it would be 2 to the n. I mean, it is true that sort of, yeah, in a way, you know, if you fix xi equals 0, you can kind of eliminate one variable. Or actually, you can just take, yeah, you can probably make it 2 to the n. I mean, you can sort of fix a variable, or, you know, you can just consider all subsets of xi equals 0s to throw in to get m up to n. So you can consider all like n choose n minus m coordinates to potentially be these like xi equals 0 coordinates. So yeah, good question. You could get this down to only 2 to the n. Okay. Great. So that's actually the end of search. So if you have feasibility oracle, you can actually find points in the polytope. And last one we'll talk about is optimization using a feasibility oracle. Okay, so this is the problem again. You just imagine you have the ability to decide feasibility of k, or we can also imagine we have the ability to solve search, but we're really only going to need feasibility. And here the task is you want to find a point x that maximizes a given linear form c dot x. Or you can also just think about the task of finding the maximum value c dot x achievable, not necessarily the point x that achieves it. But we can do both. So if you have an idea for how to do this, a quick idea, type it into the chat, and we'll see if you get the right idea. But here's a picture. Let's say we're in 2 dimensions, and we use our feasibility oracle, and we're like, yep, k is feasible. It's, you know, it's not the empty set. And now we want to maximize c dot x. So c is itself an n-dimensional vector, and you can think of it as an arrow. And you know, all the points in R2 that make a given value for c dot x, they look like they're on these like dotted lines. Or in general, like all the points in x and Rn that make a given value for c dot x are on a hyperplane. Okay, and maximizing c dot x over this k is really like about finding like the farthest extent of the polytope k in the direction c. That's the point you're trying to find. It's the maximizer. Okay, and the maximizer always occurs at a vertex. There's a little caveat there, which we'll come back to in a moment. Well, it's a quick moment. I guess it's right now. The maximizer always occurs at a vertex unless k is unbounded, in which case it's possible that the maximum is infinity. Okay, so here's a picture of this in R2. Here's an unbounded k. That's a perfectly valid feasible set. And in this case, the maximum value of c dot x is infinity. You know, this c dot x, there are x's that can make c dot x arbitrarily large. Okay, so that's actually, you want to be able to detect that if you can, if you're trying to maximize c dot x. But if the maximum is not infinity, then the maximizer will occur at a vertex. And we know that these vertices can be written down with polynomially many bits. We've seen that before. All the vertices can be, which means that just given k, there is some number m, kind of like the big box value b, actually, of size 2 to the poly k, which means you can write m down with polynomially many bits as well, such that the max is either at most m or else it's infinity. So like we kind of know that if the maximum is infinity, fine, it's infinity. But if it's not infinity, then it has to be occurring at a vertex, and this vertex is, polynomial bit complexity. So the maximum value is either infinity or at most some number m that you can write down in polynomial time. Yes, I see somebody in the chat had the right idea for how you can do this optimization. Spoiler, it's going to use binary search, but a little bit more actually. So this is good. So actually, this means we can use the oracle to detect if the answer is infinity or not quite easily. We just have to figure out this number m, which is polynomially many bits. And we then ask the oracle, hey, is it true that k together with c dot x is at least m plus 1 is feasible? Okay, and if this is feasible, then it must be that the maximum is infinity, which is great. So we've used the feasibility oracle to decide if the maximum is infinity. And then if the oracle on this new set, k union c dot x is at least m plus 1, comes back and says infeasible, then you're like, great, the solution is going to be finite. And in particular, it's going to be at most capital M. And now we can get started, as mentioned, with binary search to try to find this maximum value. Okay, so let's now assume we're in the case where the maximum we know is at most some m, which can be written down with polynomially many bits. And we can also do the same thing just to get started for binary search. We can ask if c dot x is able to go to minus infinity. Actually, even if it's not, we can just put in some big box constraints. So let's just assume we also have this number minus m, that we know the maximum is at least this. And now we can binary search. So we can use our oracle on k together with a single inequality of the form c dot x is at least t for various values of t. So we can start t at like the big capital M, and we can also try it at the like really small minus m, and we can start halving, right? So we'll use the oracle to ask, hey, can you get a point in k that's beyond this half space, c dot x equals t? No. And you ask about this one, and you find out, yes, k has a point that's bigger than this hyperplane. So then you ask in the middle, does k have a point bigger than this hyperplane? Yes. Does k have a point bigger than this hyperplane? Yes. Does k have a point bigger than this hyperplane? No. So you go back, and you know how binary search works. And all the while, you're narrowing in, zooming in on the optimal possible value for c dot x among points x that are inside the polytope k. And that's great because you're like having, the range of number of values. Let's say m starts out as like an integer that's 2 to the poly size of k. It says polynomially many bits, so you can kind of, get 1 bit of accuracy per halving on the optimal value of c dot x. I got a question in the chat. Does this always return a vertex? No, that's a good point. So as you're going along, we'll come to this in a second. As you're going along, once we, let's say, try this one, I don't know if I have one more example, and we decide, oh, k together with c dot x is at least this t is feasible. We know using search, we can get some point in this little triangle. So we can get some point in x, which achieves at least this value of t. But we'll see in a minute this question about whether we can actually pick out this vertex that's the maximizer. We'll come back to that. Yeah, as Misha says in the chat, this can only return things which are of the form integer over 2 to the k. That's right. If you assume that like m starts out as like an integer, and you're always sort of binary searching with this t value, t will always be of the form like integer over 2 to the k. It'll be like a dyadic rational. And you can see, you'll be getting like one more binary digit of precision. You can see that, if, k involved like some numbers like 3 and stuff, the optimal might not be a rational number whose denominator is a power of 2. So there's a little bit of a wobbly thing going on here, but we'll come back to that. The point is that you can get within epsilon of the maximum very efficiently in a number of steps that's polynomial in the input size, polynomial in the number of bits of k, and polynomial, in fact linear, in the logarithm of your desired accuracy epsilon. Okay, or in other words, if you want like R digits of precision, R binary digits of precision, you can do that in poly R, in fact, order R, multiplicative running time factor. Okay, which is really great. You have this super fast, quadratic convergence. You're getting extremely good answer, accurate answer for the optimum possible value of C dot X. And you can use search to find a point X in K, which achieves this near max value. Great. So if you're happy with that, great. I mean, you can just take that. And in many cases, like definitely in practical, like, I don't know, optimization, industrial optimization applications of linear programming, this is perfectly fine. Well, I was going to say you're probably not doing this in industrial applications. You're using some pre-written hyper-optimized package. But anyway, if you're happy with getting within, like the correct answer to within 2 to the minus n squared, which you can certainly do by taking epsilon to be 2 to the minus n squared. That'll only incur an extra n squared factor in your running time. Then that's great. But sometimes you're really greedy and you're like, man, I really wish to know literally the exact rational optimum. And I'd even also like to know like a vertex which achieves this exact optimum. This you can do as well, but kind of surprisingly, and it's sort of maybe a little known fact, you need some hackery at the end. In particular, you need some like number theory. So I'll just talk briefly about this. I'm not going to get into the details, but I'll just talk briefly about it for interest's sake. Basically, the story is we kind of know in advance, right, that the vertex is like a rational number. It can be expressed as with rational numbers whose denominators and numerators are integers with polynomially many bits. But we don't know what that denominator is. And you can't try all denominators or anything because there are exponentially many possible denominators. By the way, this is like a really pedantic point. Like I love pedantic points, as you know. But this is a really pedantic point. So if like this is kind of not interesting to you, then just forget it. But if you're interested, what we can get is like an extraordinarily good, binary representation of this fraction a over b, this optimizer. So we're kind of, there's this unknown fraction, the optimal value of c dot x. We kind of know that the denominator can be written with some, polynomial n bits. And we can get like an amazingly accurate like decimal representation or base 2 representation of this. And we just kind of want to like round it off to the nearest fraction whose denominator has at most n bits. And this is another like number theory task that can be done in polynomial time. Like I give you like a denominator upper bound, and it's like n digits, and I give you an extremely close, like poly n close, decimal or binary representation of this fraction, and I say like, tell me the actual fraction. This can be solved using continued fractions. It's actually not that hard. It's basically, I'm not going to get into it, but it's basically like doing Euclid's GCD algorithm, but in an approximate form. And suffice it to say, you can do it. So I'm going to skip that. But like when you really want to get exact optimal value of c dot x, you get like super, super, super close to it with a dyadic fraction. And then the last step is some like rounding thing. And as one more bonus exercise for you, I'll let you think about this one. You might wish to also find a vertex which achieves this optimum value. And once you know the optimum value, you might think, oh, I'll just throw in a constraint saying c dot x equals that optimum value. But this doesn't quite work. What could happen is the c might actually be parallel to some facet of k. So your solver that gives you back a feasible solution might give you something in the middle of the facet instead of a vertex. But exercise for you, you can actually find a vertex by like very slightly perturbing c. Okay, so everything on this slide and the last slide are kind of very pedantic points. I just tell them to you for your own interest's sake. But the implication is that, all you need to be able to solve is this feasibility problem. And then by reductions, you can get everything you want. You can get solve the search problem. You can find the optimization problem. You find the exact optimizer, the exact optimizing vertex, and so forth. And let me just end with like one slide about this number theory thing. There's even further advances in linear programming. We'll talk about them actually. When you want to solve the linear program without actually knowing the linear program, you just have some like a separation oracle, it's called. So some general case, and in order to solve that, you need like some very sophisticated number theory problem that you need to solve, something about Diophantine approximation. And like, here's a part of a handwritten letter from, it was like Grötschel, Lovász, and Schrijver who did this originally in the 80s. And here's a handwritten letter from Lovász to Martin Grötschel saying, "Dear Martin, I think I found a polynomial." They didn't know how to do this like last Diophantine approximation step, this very sophisticated number theory in polynomial time. And he said, "I think I found a polynomial time algorithm for simultaneous approximation. Consequently, to compute the affine Hall of a rational polytope, given a strong separation oracle," I enclose a write-up. So actually, this is the origin of the so-called LLL algorithm, this number theory algorithm about geometric lattices. And it was all developed, well, Lovász developed it. He's one of the L's in LLL. It was all developed to get over this like last weird annoying hump in like a linear programming problem. Okay, so I'll stop there. I guess I'll, in fact, stop the recording there, but I'll stick around. So if anybody wants to ask questions, I'll still be here.